Okay, so let's start talking about Chapter 10, the chi-square test. So in class I will cover a little bit of Section 10.1 and basically most of Section 10.2. That's all we need to cover in Chapter 10, okay? So the first thing that we need to know, when we're doing a chi-square test, we're no longer working with the normal distribution. We're working with what is called a chi-square distribution, okay? So this is what a chi-square distribution look like. Actually, we're looking at 4 of those right now. First thing that we can notice is that those distributions are not normally distributed, so they're not symmetrical, okay? So they're always right skewed. So a chi-square distribution, always right skewed. That's the first thing. The second thing, it cannot be negative, okay? Look at the x-axis. All the 4 distributions that we have here, they don't go below 0. So it has to start at 0 and be positive, okay? So our chi-square value cannot be negative, okay? So that's the first thing. Throughout Chapter 10, we will work with level of significance. So this is a chi-square distribution. Sorry if the picture is blurry a little bit. And often I will ask you to use a significance level of 0.05, maybe even 0.01. So basically what this means is that if we're looking at the right tail, okay, it's a right skewed distribution, we're looking at the tail. If a significance level is 0.05, it means that we have 5% in the tail. So that's our critical zone. We are interested in that 5% to see if our chi-square value will fall within that critical zone. Okay, so the significance level is the same as the area of the critical value in the right tail. Okay, so this is what I've decided to do to show you a little bit what chi-square tests are. I will perform one for you. I'll give you very little details because all of this will cover it in class, but this will give you a general idea of what a chi-square test entails. Okay, in section 10.2, we are only focusing on tests of independence. Okay, so that's the only chi-square test that we are doing. So in section 10.2, you'll get problems such as this one here. Okay, so do some college majors require more studying than others? The 2009 National Survey of Student Engagement asked a number of college freshmen what their major was and how many hours per week they spent studying on average. A sample of 1,000 of these students were chosen, and the number of students in each category are presented below. Use a 0.05 significance level. Okay, so the first thing that we need to do when we're doing a chi-square test, more specifically a test of independence, we are testing whether there's a relationship between 2 qualitative variables, okay? So here, the first qualitative variable is the college major, and the second one is the amount of hours studying, okay? So, and you will understand why this variable is qualitative in a sec, okay? So this is called a contingency table. This kind of table will always be given to you in the problem. So we have our first variable, major. So we are interested in 4 different types of major: humanities, social science, business, and engineering. Okay, and our second ordinal variable is hours studying per week. So we gave the students an option. So did you study between 0 and 10, 11 and 20, more than 20? Choose one of the categories. So this is why this is a qualitative, more specifically ordinal variable. Okay, so this is how the problem would start, okay? Even though it's called a chi-square test, we're still doing hypothesis testing. The only difference is that we're no longer working with the Z or normal distribution, we're working with a chi-square distribution, okay? So set my null hypothesis. My null hypothesis is as follows. There's no relationship between major and hours studying per week. Okay, no numbers here, no relationship. So the 2 variables are expected to be independent, so no relationship. Whereas for alternative hypotheses, there's a relationship between major and hours studying per week. So the 2 variables are dependent, they are related. Remember what I said, every time you'll have a problem like this, you will be given a contingency table. Okay, and the contingency table looks like this. So basically in this table, the numbers that are identified are called observed frequencies. Okay, those are count. So for example, in the category of humanities, there are 68 students that reported studying between 0 and 10 hours. Okay, so that's a frequency, that's a count, that's a number of student. Okay, and that's the same way for all of the other cells. Okay. What I need to do is get the total for each columns and cell, which is what I did on this slide here. Okay, so if I'm looking at the row for 0 to 10, I added all of the values and it gave me a total of 345. Okay, so I do this for each row, for each column. Okay, and if you're looking at the cell here, the grand total is 1000. So if I add all the totals for the columns or all the totals for the row, both of those totals give me 1000. So that's my sample size. I have a sample of 1000. Okay, so this is what I start. I have observed frequency, I have total. Now I will use the total and my observed frequencies to calculate expected frequency. Why do I need expected frequency? And I'll explain what expected frequencies are later in class. I need expected frequencies because of this formula here. This is how I get the results of my chi-square test. So I need to know O, which is observed frequency, and I need to know E, which is expected frequency. Okay, so let me show you how to calculate expected frequency. Okay, so in order to understand, I'll go back here to this table. Okay, so first thing that I need to understand, for each observed frequency, I will have an expected frequency. Okay, so the way I do it is, so if I'm looking at number of hours studied per week, so 0 to 10 and humanities, so observed frequency of 68. I need to calculate an expected frequency. How will I do that? To get the expected frequency to this specific row, I will take the total of that row times the total of that column, and I will divide it by the grand total. That will give me the expected frequency. Okay, if I want the expected frequency for this cell more than 20 hours per week in engineering, I will take the total for the row times the total for the column, and I will divide it by 1000. So that's how I would do it. Okay, so let's look at what those expected frequencies would look like. Okay, so let's look at this here. So this is what I've done here. I really like to work with a table when I perform a chi-square test. Okay, so this is the table that I worked with. So first of all, my first column includes all the categories that I had in my previous table. Okay, so students who reported studying between 0 and 10 that are in humanities, 0 and 10 social science, 0 to 10 business. So I have all of them with the observed frequency for each of those. Okay, so this is listed, and I have a total number of students in this study of 1000. Okay, as I said, what I'm interested in recording right now or computing is the actual expected frequency. And I mentioned that in order to do this, we need to do total row times total column and to divide it by grand total. Okay, so if we're looking at the first category here, I wrote down the information that I needed. So I had a total row of 345 times total column of 257, and I have a grand total, a sample size of 1000. If I calculate this, it would give me 88.7. Okay, so the 88.7 would be my expected frequency for this specific category. Okay, for the next one, 0, 10, social science, this is how I would do it. Okay, so the value would change a little bit, but the formula would not. So based on the table that we had 345 for the total row times 261 for the total column divided by the grand total, and it would give us an answer of 90.0. Oops, there you go, 90.0. That would be our expected frequency for this specific category. Okay, so I will do everything for you quickly and I'll be right back. Okay, so now I've calculated all my expected frequency. So each expected frequency is written right next to the observed frequency for that specific category. One thing that is really important to make sure that you calculated the right expected frequency, if you add the total of the column for expected frequency, your number will always be equal to the total number of observed frequencies. So it's the same as the sample size. If it doesn't equal that, you've made a mistake somewhere. Okay, so that's the first thing. Now we're ready to actually perform or complete the next columns. Okay, so the column after that, we take the observed frequency minus the expected. So here for the first category, we would do 68 minus 88.7. That would give us minus 20.7. Okay, so instead of completing this entire column, what I like to do to save a little bit of time is to actually finish my entire row. Okay, so my next column is I square the results that I just got. So minus 20.7, if I square, I lose the negative value. It gives me 428.49. Okay, and then the final column, I take this score and I divide it by my expected frequency, which should give me 4.83. Okay, so there you go. Now I have all the information that I need for the first category, and I will perform this for every single category until this table is fully completed. Okay, so I'll complete this and I'll be right back. Okay, so now I have completed all my table. Okay, so that's a lot of numbers because I have a lot of categories. Okay, so if I scroll all the way down, there are two things that actually I can do to make sure that I haven't made any mistakes with my math, with my calculation. First of all, if I looked at the column O minus E, which is this one right here, and I add this total should give me very close to 0. Okay, so it should always give you very close. What is very close? Well, actually, if I add all of my total up, I will get this. Anything more than 0.2, you've made a mistake probably somewhere. Okay, so right now we're on the right track. What I'm really interested in, however, is the score, the total of this, because the total of this column here is your chi-square score. Okay, so if I add all of this column, I get a score of 34.67. That is my chi-square score. I have a chi-square score of 34.67. So all of this table only was used to only get this specific score. Okay, the total score of the last column. Okay, so now let's make sense of this chi-square result. Okay, so now we have a significance level, or not a significance level, but a chi-square score of 34.67. So before we can decide whether we reject HO or fail to reject HO, I need to identify critical value. And this step is a little different than when we're doing hypothesis testing. With hypothesis testing, we just look, it's always the same value. In this case, in chi-square, when we're doing a chi-square test, it will depend on the numbers of degrees of freedom. Okay, so I'll teach you in class how to calculate degrees of freedom, but here we have 6 degrees of freedom. So with this information, I go in my textbook to table 8.4, okay, and I look for 6 degrees of freedom. For a significance level of 0.05, I have a critical value of 12.592. So that's my critical score, okay? So I want to know if is my chi-square score bigger or smaller than this. Because my score is bigger than the critical value, okay, so 34.67 is bigger, my conclusion is as follows: I reject HO. Therefore, our two variables are related, so there's a relationship between the two, okay? And this is the end of your chi-square test, okay? So this is what I want you to do for next class. This is an actual contingency table, so you don't know what the problem is all about, you don't know the significance level. But what I would like you to do is, I would like you to calculate the expected frequency for the 8 different cells that we have in this contingency table. So next class, I would like you to come with 8 expected frequency, 1 for each cell, just to make sure that you understand how to calculate expected frequency. Okay, so if there's any question, don't hesitate to email me, and if not, then I'll see you in class next week. Okay, see you soon.